We hear these crazy numbers all the time. Billions of transistors packed onto a single microchip. But have you ever stopped to wonder how we get from a single transistor to, well, that? It's not just about making things smaller. It's a whole different way of thinking, a complete revolution in design. So today, we're going to pull back the curtain on the clever architectural tricks and the fundamental building blocks that make all of modern electronics possible. So the very first thing you have to get your head around is that the entire rulebook for circuit design got thrown out the window. Back in the day, with big, clunky, discrete circuits, transistors were the expensive, precious gems. You'd use as few as you possibly could, and you'd surround them with dirt-cheap resistors and capacitors. But on an integrated circuit, an IC, it's the complete opposite. Transistors are basically free. You can stamp out millions of them. But resistors and capacitors, oh, they are absolute space hogs. They take up so much valuable silicon real estate. And that one single shift, well, it changes absolutely everything. And that leads us to the big question, the puzzle that every single IC designer has to solve. If your most expensive component is now free, and your cheapest parts are now way too big to even consider, how do you build anything? You have to get really, really creative. All right, so here's our game plan for this explainer. First, we're going to dive into that new design philosophy that this new reality forces on us. Then we'll look at three absolutely essential building blocks. A circuit that's basically a current photocopier, the basic gain cell that gets you amplification without resistors, and the wild trick for stacking transistors to get insane amounts of gain. And then we'll wrap up with a quick peek at some advanced engineering tricks of the trade. Okay, let's jump right in with that new philosophy. So welcome to the world of silicon real estate, where every single square micron on a chip is precious. The new philosophy is actually pretty simple. Transistors have to do everything. They're not just for amplifying anymore. Nope, they become our resistors. We call these active loads. They become our current sources, providing the precise power and bias for other circuits. And because we can't use those big, bulky capacitors to filter things, all the circuits on a chip have to be direct coupled. That means they're wired straight into each other, no separation. It's a completely different universe of design. And, this new way of thinking immediately creates our first huge problem, biasing. Think about it. If you have thousands or millions of little amplifier stages on a chip, how do you give each and every one of them the exact, stable operating current they need to work? You can't just slap a resistor network on each one. You need something way more elegant. And that elegant solution is a genius little circuit called the current mirror. The idea is brilliant. Think of it like a photocopier, but instead of paper, it copies electrical current. You create one super precise master reference current, and then the circuit just cranks out as many perfect copies as you need to power everything else on the chip. So how does this magic photocopier work? Well, it's actually pretty simple. You take two transistors that are perfect twins, absolutely identical. You force your reference current through the first one, which is wired up in a special way. We call it diode connected. This sets a very specific voltage on its gate. Then you just connect the gate of the second transistor to that exact same voltage. And because they're twins, that voltage forces the second transistor to conduct an identical mirrored current. It's just beautiful. And this whole technique has a name. It's called current steering. It's this incredible ability to generate one single master reference current and then steer perfect copies of it wherever you need them all across the chip using nothing but a few tiny transistors. It's a total game changer. Okay, so biasing. Solved. Check. But what about the whole point of an amplifier? Getting gain. How do you get a ton of amplification if you're not allowed to use big resistors, which are kind of the key to gain in the old discrete world? This is where that transistors do everything mantra really starts to pay off. You just rip out that big imaginary resistor and you replace it with, you guessed it, another transistor. This one is set up to act like a perfect current source. We call this an active load, and it gives you an insanely high effective resistance. So you get tons of voltage gain, but it only takes up the space of one little transistor. Now, this brings us to a really fundamental concept, kind of like a law of physics for transistors. It's called intrinsic gain. The best way to think about it is like a speed limit. It's the absolute tippity-top maximum voltage gain that any single transistor is physically capable of giving you, even with a perfect active load. It's baked right into the physics of the device itself. And what's really interesting is that this speed limit behaves differently depending on what kind of transistor you're using. For an old-school BJT, the intrinsic gain is pretty much a fixed number. It's locked in. But for a MOSFET, and that's the heart of pretty much every modern chip, something really cool happens. Its potential gain actually goes up the less current you run through it. This gives designers this amazing knob they can turn to trade off between speed and gain. So, now we've got a gain cell that can hit that theoretical speed limit of a single transistor. But what if that's not enough? What if your application needs even more gain? How do you break past that fundamental limit? It seems like a trick question, right? I mean, if you're already at the absolute maximum, how can you possibly go any higher? The answer is one of the most powerful and, honestly, coolest tricks in all of analog design. You don't try to make one transistor better, you just stack them. The technique is called cascading. You take your main amplifying transistor, and then you stack another one right on top of it, almost like a shield or a bodyguard. Now, this second transistor, its job isn't to amplify the voltage. It's just a current buffer. Its only purpose in life is to shield that first transistor from any annoying voltage changes at the output. And this simple little trick makes the output resistance just skyrocket. And here is the absolutely incredible result of that. When you stack them, you don't just add the gain together. Oh no, you multiply it. The total gain of a cascode amplifier can get close to the intrinsic gain squared. I mean, just think about that. You've taken the speed limit of a single transistor and you've squared it, all by just adding one more tiny device. It's amazing. Okay, now that we have our core building blocks down, let's take a real quick peek into the Pro Toolkit at a few advanced versions that solve some very specific problems. First up is the Wilson current mirror. This is basically a souped-up deluxe version of our basic current photocopier. It cleverly uses an extra transistor to create some negative feedback, which makes the copied current way more accurate and a lot more stable. Then there's the Widlar current source. This thing is just brilliant. It solves a really common problem. How do you create a teensy tiny current, like in the nanomamp range? Normally, that would take a resistor the size of a football field. But this design uses a tiny resistor and some transistor magic to generate that little trickle of current, saving a massive amount of chip space. And finally, the Darlington pair. This is kind of like cascoding, but it's for current gain instead of voltage gain. You wire two BJTs together so they act like one single super transistor. And its current gain is roughly the two individual gains multiplied together, beta squared. It's just a really simple way to get enormous current amplification. So let's just pull this all together. These three core techniques we talked about, they are truly the DNA of modern microelectronics. You've got current steering for elegant and efficient biasing. You have active loads, which let us get huge gain without those big clunky resistors. And you have cascading, the magic trick for multiplying gain way past what a single transistor could ever do on its own. You know, mastering these fundamental blocks is like learning the alphabet. Once you know them, you can combine them in endless, countless ways to write sentences, paragraphs, and entire novels of incredibly complex integrated circuits. They are the absolute foundation that almost every analog chip in the world is built on. So the only real question left is, what will you build with them?